Can you hear me?
Hello? Yeah, I can hear you.
Hello, hello. Can you hear me?
Hello?
Yes, no? Okay, good. Thank you. Thank you. Thank you.
Hello?
Oh, I didn't. Okay. I see. I have to go. Why is it? Okay. Can you try again?
Testing.
Dan?
Hello?
Thank you, Daniel. Thank you.
Hello?
Nice to hear. Yes,
Okay.
yes. Perfect. Thank you. Nice to hear your voice. Great. All right. One is good. Any questions? Administrative questions? How to pass the course questions? Work hard. I don't know, like put courses on Piazza. Yes, not enough people do it. And I pay the guy 1 hour a week. So he has plenty of time to help you on Piazza. But he doesn't need to because nobody puts questions. So please, if you can put some questions, that would be nice. So we can justify our existence as instructors. Okay, very good. Let's see, what's the question? No question. All right, I mean, I know I put a lot of homework, but remember there's a midterm. So some of the questions are meant for the midterm. They're not all for next week. So don't scare too much. Yeah. Okay, so same thing next week. I'll put a little bit more, but again, it's mostly meant for the midterm. Okay, I need to have clay to make a pot. Yes. All right. Let's go. Yeah, so Lagrange multipliers, how many of you have seen it? How many? Okay, 1%, two. So 235 people haven't seen it. Is that true? Did someone take 235? Did you take 235? Yeah, did you see Lagrange multipliers? Okay, good. Yeah. Yeah, so I don't know what we're doing then. I guess we're gonna make it more rigorous. Good. All right, so yeah, that's the picture. You have a surface and you have a constraint given by this function g, and then you want to find the minimizer on the blue curve. You see this little blue curve over there, right? That's Lagrange. Oops, let me make it very strong. Let me make it even stronger. No, it's too strong. So there's some crazy curve, and on this crazy curve, we're trying to find which value is the smallest, and it's this dot down there, right? In this case, the maximum. All right, so try to think 3D from now on, and this is a good picture to have in your head. Okay, good. And we are trying to find these 2 points, and we will use the tangent space. This is way too big. Yeah, we will use the tangent space. Okay, so this planes will tell you where the max, min are, stuff like that. All right, let's start. What is the tangent space? People on Piazza were asking. So let's once and for all clarify it. Yeah, okay, so what's the problem? The problem is you have a function and here's a constraint, just the unit circle. And so this is the unit circle over here. Okay. And yeah, so this blue line, we'll talk about it. No, I've talked about it before. This is called the tangent line. So in 1D, you already know this from first week. This is the tangent line given by the gradient of G. Okay. Yeah, I'll define it carefully. And then the red curves are the direction of the gradient. Now, can someone remind me where does the gradient point to? It points to what? We talked about it in class. I proved it. So, any ideas? Any guesses? To the what? No. The what? The maximum what? Yeah, exactly. So, yeah, I will it your way. So, the maximum, let me call it increase. Okay, it's the direction to which the function increases the most. So when the red is not perpendicular to the blue, that means this is not a local min. Because if it was, it would be normal to the blue line. So that the entire week would just be talking what she mentioned, that we will prove that this guy is a local min when the gradient is normal to this blue line. That's it. Entire week's material. Yeah. Okay. So, and that's the intuition that if we was a local min, this would be the direction of greatest increase. Okay. Questions? No, what are you talking about? 235 and 237 both did Lagrange. No, 257, I know, I took it, and I didn't learn it. But I don't know what we learned. I know I learned something about geometry. I don't know. Maybe we learned it in abstract. Yeah, so if it's not perpendicular to the target, then then it's not the local min. All right, because of that intuition that the gradient points to the greatest increase. So that guy was not the, and then minus of the gradient points to the greatest decrease. So so that's why it's not local min. Okay, I don't know. That's the intuition. We'll prove this stuff. Right. So but going back again to what she said, when you have a graph and this is the level set of the function. So this guy was gx squared plus y squared minus 1, and then this guy is the level set, right? So this is L0. So where g is 0. Indeed, we said that nabla of g is perpendicular to the tangent, right? I mean, we can, I mean, it was in your quiz, it was all over the place. So I don't know what to say. So this is the thing. And then, but so 1 plus 2. So to have to have x naught to be a local min, we want gradient of f to be parallel to gradient of g, and here's the Lagrange multiplier equation. Okay, that's it. That's the geometric intuition of Lagrange multipliers. So again, to have that this point x naught is a local min, you want your gradient to be parallel to the gradient of G. Okay? And yeah, because we always know that this guy is perpendicular to the tangent space, which I will define. Yeah, I know well, not quite. I didn't run Riemann tensors. All I did was differential forms for the most part. Okay, and metric spaces. Right, so perpendicular, right. Yeah, and we know that this guy's perpendicular to the level set. In other words, we want the gradient to be parallel to the gradient of the constraint. Okay, so that's Lagrange multipliers in a nutshell. And this guy is the Lagrange multiplier. Yeah, so I have to define the blue line. So there was a blue line, and we had that the blue line is perp to that, I will call it in a second, this guy. And so we will prove the Lagrange theorem is the same as that this guy is perpendicular to the, and this is much easier to check. So that's what you will see in the examples. It's basically a dot product. So this will be gradient of f dot v equal to 0 for all v in the tangent space at x naught, the blue line. Okay, so pictorially, here's the picture, here's the vector v, and here's the gradient f. If this normality is satisfied, you have that x naught is a local min. Okay, yeah. All right. Oh, I had metric spaces. It was pretty cool. All right. So first, surface. What's a surface? We won't do the abstract stuff. There is an abstract definition, but there's no time for that or point. We will define a surface to just be the level sets of all these functions intersected. I will do an example right after, but that's what you should have in mind because that's what we care about. So, for example, the simplex is what? Is all x in Rn. So that summation of xi minus 1 is 0. That's a surface, right? And we talked about this a lot. And yeah, it's on your homework as well, right? You know your homeworks. Yeah. So this is a surface. That's what we mean by surface. If you can write it in as a 0 level set. Yeah, I mean, we're not going to talk about. Does anybody know what a manifold is? Alex? Yeah, okay. It just means locally. Well, no, you don't know. You've taken it? Oh, are you guys talking about manifolds? Yeah, that's fun. So let me tell you, because I mean, it shows up in data. So it's not like a mathematician's dream. So it just says that if you have some crazy set and you zoom in, okay, it looks flat. Okay, that's what the manifold is in rough terms. So you go in and it looks flat. That's all. Like if you take a derivative, it doesn't matter. But for your intuition, that's how it was taught. If you just go in very, very closely, it looks like Euclidean space. Okay? All right. Very good. Yes. Manifolds are cool. All right. Let's talk about tangent space then. Yeah, so all right, first I need this notion. Yeah. So CK differentiable curve. Let me give you some intuition. So Suppose your guy M is this guy. So this is M, just x squared plus y squared minus 1 equals 0. Then a differentiable curve would just be like you fix a point, like over here, and you move forwards in time, like up to here, xt. Okay? So this red part will be intuitively what a curve is. Okay, so mathematically, here's the mathematics. Mathematics is just a function, so that the range of this function is always inside the surface. Okay? So there's many, oh, I wish I could give you a nice, there's a nice picture I could show. Here's for my research. So you have like a loop or a surface and it's inside the sphere. Okay? Yeah, that's pretty cool stuff. So anyways, that's a curve inside the surface. So far, you've seen this stuff, that's a function, right? But now we're doing more advanced things. We're talking about functions whose range is inside the surface. Recall implicit function theorem. In implicit function theorem, we gave you some graph and we asked you to find a graph within the graph. Remember? So here's an example, stupid example. So I need something that's not a function, like this. So this is not a function, but by implicit function theorem, there are two functions here. So there's this guy, f minus or f plus, and then there's the other function, f plus. This is okay. So, anyways, is that all okay, everybody? Is that okay? Does that make sense? Okay, just intuitively. I'm not proving anything. I'm just throwing a lot of words together. So hopefully, yeah, you can. So now we're going to make some big jumps. I hope I can keep you with me. All right, so tangent vector at point x naught. So always please go back to the blue line. It's really the simplest example. So this is x naught, and this line over here, this will be the tangent space. Okay, so whenever you get lost, go back to this example. So what are these? I know it's going to be very complicated. I hope you can follow. So here's what you do. From the point x naught, you start a small curve like this, x of s. This curve x of s is differentiable, so it has a derivative, right, in s. And you compute its derivative at the point x naught. And this vector will point this way. So it will point like that. This will be a v equal to x dot s at s equals 0. So it's not, okay, let me do it, what you cannot have. So because the curve is curving, x dot will not go like this, right? So not possible. Because remember, x dot points to greatest increase. And the greatest increase is getting curved inside the surface. I mean, that's the definition. I'm not proving anything. Like that's how it's defined. And because you might see this, I don't know, this. Yeah. I mean, you will be amazed if you read a bit of data analysis. Like if you go to blogs, everybody tries to define these things, and now you learn it formally, but they give you heuristics. So, anyways. Yeah, you need a lot of math. Sure. All right. And anyways, so yes. So all these vectors that we just drew give you what is called the tangent vectors. But then if you put them all together, the set of all these tangent vectors will be called the tangent space. So I just want to go here and then talk about in detail. So again, we fix a point. We fix a point x naught, and then you will have a bunch of vectors. So let me draw it really big over here. And you will have all kinds of vectors. You will have, this is one vector, this is another vector, is another one, is another one, is one more. All right. These are all vectors tangent to the same point, and they all belong to the txm naught. Any guesses what this space is equal to for this example? Like this collection of vectors, what do you think they are? Huh? Sorry, what? What? No, it's just to realign. Like, actually, let me do this example. You know what? Let me do this carefully because I think you guys are completely lost. All right. So, again, let's do this slowly. Actually, I've typed this. I don't know why I'm talking about it. I have it right after. Sorry, yeah. I remember. Yes, right here. All right. I went straight to the sphere. Yeah, it's brutal. Okay, I'll keep coming back to. So again, this is the example, but I will keep coming back to 2D. This is way too advanced. All right, this is the sphere, right? So all the points that are equidistant from the origin, right? Euclidean distance 1. And I'm going to compute some tangent spaces. Yeah, so in R2, we just have the circle. All right, just the circle over here. All right, yeah, so we're doing 2D, exactly, yeah. So remember, right, the circle can be parameterized by cosine t and sine t for t in 0, 2 pi, right? Like if you put t equals 0, you get this guy, right? So this is a curve, x of t, and it starts from here, x of 0, and it goes like, goes here, this is x of pi, right? Yeah, and then x of 3 pi over 2, and then over here. Is that okay? So I gave you the curve. Now by taking its derivative, I'm going to find you the tangent vectors. Okay? Any questions so far? All right. So this is the parameterization, like an arbitrary point, x naught. Because, right, if you put x equals 0, you get cosine s naught, sine s naught, which will be some point that you like. Maybe you want it over here. Okay? I'm just doing it for generic points. Of course, I can just put 0, 0, but I want to give you the tangent at every single point along the circle. Yeah? Is that okay? Okay, good. Yeah, so we have to find its derivative. That's pretty easy. So derivative of this guy is sine, this guy is cos, and you plug in your guy, so you get this. Yeah. And then remember, the definition of the tangent space is that T of x naught are all these points. So yeah, so all these V's equal to x dot at s equals 0. So these are all the vectors possible. Well, okay, let me first give you the space. So yeah, so in other words, it would be the span of, can I call this V or do I have to let me write it, fine. Minus sine S naught, and then cosine S naught. But let me put some numbers there because this is way too abstract. Let me put 0, 0, okay? So if you put S naught equals 0, you get X naught. What's X naught? Just to see if you follow. Yeah, thank you. So it's this guy. All right. And can someone else now tell me what's the tangent vector? Huh? Yeah, thank you. So these vectors are, yeah, let me, where should I put it? The point, so you basically take the y-axis and you move it over here. Let me do it blue as usual. Okay, this is the 0, 1. So you take the span, so this is the span from linear algebra of 0, 1. Okay, so you have all multiples of 0, 1, and you just stuck it to the point 1, 0. Is that okay? Does that make sense? No? Yeah, which part? Right, so are you happy with the vector? Yeah, and then it's just definition. The definition of the tangent space are all vectors of this form. Okay, and okay, what else am I saying? Oh, right. Yeah, let me say it this way. So now, okay, good. Let me write it over here. So again, why are we looking at span? So no more blue. So the span at 1, 0 for the unit circle would be what? Would be all the vectors in R2, so that V is equal to some gamma dot of S evaluated at S equals 0. Okay, but all such gamma are of the form lambda times cosine S sine S. Okay, so all the possible parametrizations that are contained in the unit circle. Sorry, let me not. Sorry. I have to put it in. I forgot. They all look like this for some lambda real number. Okay, is that okay? You can tell me if I, so this is all possible gammas. And then doing what I just did again before, we have what? Gamma dot would be equal to lambda times 0, 1. Is that okay? Is this okay? Yeah, so then this is nothing else but the span of 0, 1. Yeah? Is that okay? All right, good. Yeah. Mm. So, yes. So I gave you the tangent space for the unit circle. All right, good. Note the following cool fact. So x naught is equal to cosine of s naught and sine s naught. Can someone tell me why this last guy is true? Can you see why? Oh, okay, I don't know if it's obvious. Huh? Or you can just take the dot product. So you have cosine times minus sine plus sine cosine. So they cancel out. Yeah, okay. Intuitively works. It's what was your first name again? Sorry, Aggie. Abby. Okay, good. So I don't say her. Abby in the beginning, right? So that the tangent vectors are always normal to the gradient of G. That's basically the intuition here. So these are the V's, and what shall I say? Yeah, and then what is G? G is x squared plus y squared to minus 1. So gradient of G will be what? 2x, 2y. So if you parameterize, you get 2 cosine of s and sine of s. Do you understand? So this is the x of s. Oh, divided by 2. Okay? Is that okay? You can let me know. We don't have to. That's the main thing. All right, so yeah, from intuition, right? But what I'm interested for you to make sure you understand, because we'll come back to it, is that the reason this is 0 intuitively is because V dotted with the constraint is 0 because of what we proved a few weeks ago. Like Abby said, that the tangent is normal. The tangent to the level set is normal to the gradient. Remember? Okay, good. So review level set results, because we'll use them a lot. Okay, good. Yes, so right. So yes. So instead of writing what I wrote like 0, 1, it's much nicer to write it in this nice closed form, because pictorially it just says, oh, you want me to give you the tangent space, just dot with the gradient. And this makes your life 1,000 times easier. You don't have to look at curves, parameterizations, none of that. All you have to do is compute the gradient and then solve for V1, V2, right? So let me write it here for your entertainment. Gradient of G was what? 2x, 2y, and V is V1, V2. So you want this to be 0, so you want, I have to evaluate it. Okay, x naught. So I want V1 x naught plus V2 y naught to be 0. All right, and remember the guy we looked at was 1, 0 in the example. Yeah. So the equation becomes V1 times 1 plus V2 times 0 equals 0. So V1 is 0. So you get the V we talked about, 0, 1. Is that okay? All right, for linear algebra, so you have a fixed variable, V1 is always 0, and V2 is called an independent variable, right? So V2 can be any real number, right? Is that okay? All right, good. Is that okay? All right, good. Very good. So please do this. Don't do what I just did. What I did is if you have a very tough problem and you cannot parameterize, you cannot write it you cannot write it like in this no, perpendicular form. Sometimes you can't do that and you have to look at parameterizations. But in our course, you can always do it like this. So you can just solve a 2x2 system. All right, very good. So yeah, here's the counter example. So unfortunately, we cannot always have it in this simple description. Here's the counter example. So this manifold, if you look at any tangent of it, unfortunately, it doesn't. Right. So yeah, before I say that, so this guy is the same as the one before. So if you stare at it, it's just again the unit circle, same same graph. But right, this is H, and then what we just said, we said that if you want to find the V's, the tangent V's, in theory, you can compute this guy, but here's the problem. These two are no longer equal. And in fact, if you plug in the constraint, you get that the gradient is exactly 0. So you get no information because every vector dotted with 0 is 0, right? So this is useless because every V dot gradient of H is 0. But from just a few slides ago, we showed that only the guys of the form 0, 1 are in the tangent of 1, 0. So not possible to use the trick T is equal to V so that V is with H is 0. Doesn't work. Do you understand? Again, in our course, it will be very easy to find the tangent space because you just have to solve a 2x2 system. But I just gave you an example that it's not always possible. Okay, so we're doing baby steps, step by step. Okay, good. Yeah, so every vector is normal to the 0 vector, so you get R2, but we just talked about that you just get the y-axis. So clearly there's something wrong. Yeah. Right, so But I want to show you when you can do this trick. And this trick is called regular point. All right. So let's define it. First, some linear algebra. Remember, a set of vectors is called linearly independent. When you have the following equation, right? So this being 0 implies the coefficients are 0. Let me do like a stupid example. A1, 0, 1, A2, 1, 0 gives you the equation A1, A2 equal to 0, 0. So it gives you that A1 is 0 and A2 is 0. Okay? Just like a small reminder. So we're going to need this stuff. And just conventionally, if you only have one vector and you say, let this guy be linearly independent, you're just saying that it's not 0, right? Because if it's not 0, you have A1 V equal to 0, you get that A1 is 0 because V is not 0. Okay, good. All right, regular points. So again, this is a surface in our course. I know there's more general, but we're not going to look at it. And we say a point is regular if you take the gradients of them at that point, and they're all linearly independent. Okay, so let's go back to our picture. So we had this guy, 1, 0. And the constraint was g x squared plus y squared minus 1 is 0. And gradient of g is 2 times xy, right? So here you only have one vector, this guy, 2xy, which points away from the level set. And it's not 0. So it's not the 0 vector at 1, 0, right? So gradient of g at 1, 0. Yeah, let me plug it in. It's 2 times 1, 0. So it's 2, 0, which is not the 0 vector. So it is Li. Okay? Here we only have one vector, but in higher dimensions, you will have an entire plane. Let me try to draw it for you, okay? So if we did this for the sphere, like this, then you will have a plane, and right, you're just asking for all the guys to be I mean, it's hard to draw it. I'll do a MATLAB next. But anyways, so you can have more than one constraints, and you're asking it to be linearly independent. Yeah, we'll do this more carefully. It's pretty cool. At least keep, yeah, all you need to do, because, yeah, keep in mind the two-dimensional example. All right, anyhow. Yes. All right. This is the result that I just talked about, the trick. So before you use the trick, you will have to like justify it for us in your proofs. Okay. Because like I showed you, it's not always possible. So, right. So we give you some simplex, some constrained space. You compute all the gradients, and there will be some vectors, and you prove that they're Li, like take the determinant, right? Remember? So that's a quick way to find Li. And if that's the case, then you can use the trick that helps you compute the vectors. It says that the V needs to satisfy K equations. Okay. So in optimization, that means you will have K constraints, and you need to check that your V is perpendicular to all of them. Good. So that's a very nice trick. Right, yes. So in other words, we're saying that the tangent space is perpendicular. That means perpendicular to the span of the gradients. Orthogonal complement, let me say that. So let's prove that theorem. So again, I'm going to prove to you that if the gradients are Li, then you can reduce the tangent space to just computing these dot products, which is much easier. You don't have to look at the parameterizations, which is the actual definition of tangent space that you will see online if you Google it. All right. You have K constraints, and the space is n-dimensional, right? So you only have n minus k free variables. So you have n variables, k constraints, k equations. So n minus k degrees of freedom. Let me say it this way. And if you remember from linear algebra, all I'm saying, this is a subspace, and the dimension of the subspace is n minus k. All right? So, yeah, anyways. All right, this is the definition. So unfortunately, we have to go back to it just one last time. Yeah, so a V in the tangent space is of the form of being a derivative of some curve inside it, like cosine sine s. Right, and XS is inside the space. So you have this beautiful equation, which I'm going to take derivative of, right? Because HI of X is 0 whenever X is in M. All right. So we know that this guy is a 0 function. So that's why this is 0. Second step, I did chain rule. And I just plugged in the definition. This is equal to x of 0. Is that okay? So can someone tell me why am I done right away? Why can I, when I think of tangent vectors, I can just look at the gradients? What did we just, okay, let me see. Yeah, I mean, that was the statement, right? So we proved that if you're a tangent vector V, then you're normal to the constraints, right? So I got one subset, and now we're going to use some linear algebra. So again, yeah, anyways, let me do it over here. So let me remind you something from linear algebra. If dim V is equal to dim W, then V is W. Do you remember that? No? Okay. That's a nice fact. Pretty cool fact. And one is inside the other. Sorry, nobody corrected me. Like you need, how do you say it? Yeah, you need one to be inside the other, which we just got. Okay? Otherwise, just take the X and Y axis. They're both one dimensional and they are not the same space. Does that make sense? Okay, good. All right, implicit function theorem. So hopefully you remember from first week. It says that if you give me a regular point, then locally you are a graph of a function. So what else should I say here? Did I add more? Let's see. Okay. I mean, I wish I could tell you more, but that's fine. What else should I say here? Anyways, I mean, this is like second year. If you want to, you can just come and talk to me. We'll talk about it in detail. But this is quite a lot of meat here. We don't have time to do this. What shall I say? Yeah, anyways, that's fine. So just know that, yes, if you want to prove that the tangent space has a certain dimension, you need to go back to second year and use implicit function theorem. Let me give you some intuition though. Let me see. That's all right. It's too much. Okay. All right. One fact we will use is that regardless of whether you're regular or not, one is a subspace of the other. So again, because you might have forgotten what we're talking about. This guy is very complicated to compute. These are all the v's in Rn that are equal to the x dot s at s equals 0. This is hard. Okay? This guy are all the v's in Rn so that gradient of hi dot v is equal to 0. This is easy to compute. Okay? And we just proved that one is a subset of the other. And you have equal when it's regular. So in other words, do not compute this, compute this. Okay? It's too much work. You cannot sit down and find parameterizations, compute derivatives, compute span. So no. Yes. Very easy. K by n system. Yeah, so you go back to linear algebra. All right. Any questions here? Okay, let's take our break. One, it doesn't work. Oh, nice. Is that your area? Okay. Yeah. I don't care. What does it say? The position of the but it's not enough for like 50 minutes.
No, that's what I was wondering. Can I do it?
Yeah, do as long as we fill the time.
But like, that means all the content you need to do that, like,
No, no, sorry, what?
do I have, because you said you have to use the course material.
Well, I mean, okay, you can go outside the course material. Fine.
Or do I have, like, can I use some of it, all of it? 'Cause-
No, no, you don't have to use, you just have to fill the time. Yeah, I don't know what you're gonna find, but it could be like a.
What I did.
All right.
Like I was explaining what it is,
Uh,
and then I do the general. like,
That's nice.
Example, like, question, and then a maximization question.
Okay, good.
And then the way you solve it, can I convert it to the maximization question?
Right, with the
and then
minus,
solve
right,
it,
right,
so by
right.
but then that's.
Yeah, however you like it. Yeah, it's fine. Wow.
And then, so for this question, for this problem, I have a constraint where the variables are greater than or equal to 0, right?
Which section? Oh, same chapter.
Yeah, you did, it's not in here, but you showed it in class.
Right,
But the
okay.
constraint is, for each variable, it's
Yeah.
greater than or equal to 0.
Yes.
So that's a boundary point. So
Right.
you know how we did like the course, one of the topics on boundary, the minimum on the boundary, maximum on the
Yeah,
boundary
yeah,
point? I can use that, right?
Yes.
If it's just one boundary point.
Yeah. You have to speak up. My mic is dead, right? That's what I thought. Yeah, go ahead. Yes. No, that's the definition. You said need, but that's the definition. I just proved that. I mean, I didn't fully prove it, but sorry, what? I don't understand. No, tell me, like, I mean, that was the thing, right? That if they are, where is it? If they are alike, then you can compute the tangent space using that K equations, which is much easier than taking like these crazy parametric derivatives.
What happens if they're not?
Then it's not a regular point and this trick doesn't work. Because I just gave you a counterexample in the previous slide. Remember, I got the gradient of h was 0, 0. That's useless. It says every vector is tangent to it, which is false. It was false because like only the, yeah.
What if you have
Then why would you look at two of them if it's the same? It's what? Similar, you mean?
like in that case, like the gradients.
Or maybe, okay, how about this? Maybe they're the same, maybe they're different functions, but they have the same gradient. Okay,
What happens?
then we'll just have one constraint, like only one of them, right?
Why? Not other things.
Oh, because like I said, gradient of h was the 0 vector, and the definition of one vector being Li is that it's not the 0 vector. The 0 vector, does that make sense? A vector is linearly independent when you have this implication. But it means the 0 vector, you can have 1 times 1, 1, and 0, 0. And but then 1 is not 0.
Right, but what if you have a linearly equivalent that
Then it's not a regular point. I mean, I'm not saying that I covered every case. Is that in our course, we're looking at regular points.
and regarding the third, like something that like the path
Right, yeah.
that
Yeah, because like it's the constraint, like x squared plus y squared minus 1 equal to 0, right? And then, but then you constrain y to be non-negative. Huh?
that's
That would be next. It would be inequality constraint. Yeah, because now you ask me for why did you know negative. Unless you say why, it
So I
doesn't
just
matter.
wonder, like, what happens to the input? The input, like, you know,
Same thing like with the simplex, it's the boundary. Oh, no, wait, no, the entire thing is the boundary, it has no boundary, right?
I like the point.
You do it completely. Wait, what's the problem at the end? Like, what's the problem at the,
There's
like, you will have, left, you have right, you will have right derivatives, right? Because like, you can only count this way. So you will have like, yeah, you will have, just in one day, right? You will overcomplicate, right? Like you have a pair like this. So you only have like right limits. No, this would be the same, right? Because I take this to be my starting point, and it's pointing the differential curve goes inside, so it will be. I mean, just by the definition of like, yeah. Oh, because we thought maybe it's like this or like this, right? Yeah, but no, your curve has to live in the surface. Well, all right, let's go. Questions? But yeah, even if the point is not regular, we still have this trick. But it doesn't tell you the exact space, it just tells you the ambient space. So, which might be good enough in some cases, but anyhow, so. Because there was some question of why you need regular. If you want to have equal, you need regular, but if you just care, okay, what is the tangent space roughly? Then you can just do the trick. Yes, so what am I talking about? 4 points are regular. Oh, I see, yes, that's very nice. So somebody might ask you, find me the dimension of the sphere, or find me the dimension of the, so let's go up here. So you might say this, I don't know, in your later data science life. Dimension of surface. If all the x of if all x in M are regular, and dimension of the tangent space is some number M, then a dimension of M will be this little m. So the example is the one we just did. Take the unit circle. And then at every point, you have the blue line. Right? And all these blue lines, they all have Tx naught equal to 1. So you say that the dimension of the unit circle is 1. Okay? Does that make sense? So in case you see this, somebody asks you what's the dimension, that's what dimension is of a surface. All right. Yeah, I mean, but in general, that's not the case, right? Here's a stupid example. Take the unit circle and make a fat piece. Make it have a belly. So this is 1D, and this guy is 2D. And this is still a manifold. So, all right. Okay, so what am I doing with? Oh, I see. I mean, yeah, we're just gonna rephrase what we just talked about. Suppose you have constraints, and now coming back to our course, we want to find the local min over that simplex, over this nonlinear constraints. Then a necessary condition is that the gradient of the function will be normal to the tangent space. So that's what we talked about at the first hour, first 10 minutes from that picture, that in order to have local min, you need this. So you can use this as a guess point, and that's what gradient descent is, if anybody does that later. You pick the direction where it's always normal to the tangent space. So if you have some like crazy surface, you're looking, we'll do it, it's called Newton's method, we'll do this stuff. But this will come up. Right, okay. Let's prove it. Anyhow, so I'm going to prove to you that this vector v dotted with the gradient, it's 0. V is a tangent vector, so you can write it as the, you have some guy xs, then this guy v will be its derivative at s equals 0. I should put 0. I don't know why I'm putting this. All right, and we're going to do a chain rule argument. This function over here is differentiable. And we know that x naught is a minimizer, so f of xs is bigger than f of x naught. Right, so again, how shall I draw this? Let me do 1D. Suppose like this is x naught, this is the curve x of s, and it's like this. So f of x is above f of x naught. Something like that. All right. Good. So why am I doing this? Because I want to do chain rule, and I want to get the normality. So let's put the two together. This one says, so call this function g of s has min at s equals 0. So from 1D calculus, first year calculus, you have the g dot of s is 0. Okay? All right, good. So if you take chain rule of it, you get your gradient times x dds at s equals 0. Right? That's chain rule, right? Good. And you just plug in all the definitions. And from here, we are done. We just showed that this dot product is equal to 0. Okay, so what's the intuition? The intuition is locally, you have this curve x of s, and you should go back to the surface. So let me go back to that example. It's a nice example. So I will copy it and put it there because it's a nice example. Yeah, so you have a curve x of s. No, the curve is downstairs. Here's the curve x of s. And then you evaluate it, so you go up. This is f of x of s, right? And yeah, so, and locally, you know that this guy is the min. So if it's the mean of f of x, it would be the mean of this this f of x of s function. That's all. That's the intuition. That since it's the local mean for f, it will be the local mean if you go back by with x. And that's basically what we're doing in this course. You give me some constraint, I parameterize it, I map it, and then I find the infimum as a composed function. Good. This is cool. All right. All right. Questions? Yes. Wait, do you have no questions? Okay, maybe I should slow down. Is anybody on Zoom? We're going way too fast. Any questions? All right. Anyhow, so yes. But here's a necessary condition. So I give you a condition that gives you, that tells you what a sufficient condition. Now I'll give you a necessary one. Because after all, you want to find local min. So this is the surface. And yeah, so anyhow, so you have a point on that surface and you know it's a regular point. So you will have to give us that the gradients are aligned. Then I'm going to prove the first version of Lagrange multipliers, namely that the gradient of f is parallel to all the constraints, like a linear combination of the constraints. Let's go back to our example. So we had this guy, and we had this was gradient of h. And in order to have X naught to be a local min, you need your gradient to be pointing in the same direction. Why? Because gradient of f points to greatest increase. Okay, so for X not to be a local min, you need the gradient to be increasing, so you need minus of f to be decreasing the most. Okay, so in other words, you need gradient of f to be parallel to gradient of h. This is the 1D version of Lagrange multipliers. In higher dimensions, you will have tangent planes, tangent, I don't know, cubes, rectangles. So you need to be in the span of all the things that generate the space. So that's what we can approve. All right. I shall ask you questions. All right. X naught is regular. So we proved what I call the trick, that the tangent space can be written as the space as the orthogonal complement of it, namely all the V in Rn, so that HIV is 0. Okay, that makes your life much easier for finding a tangent space. We also proved that the gradient of f is parallel to the tangent space, normal, because it points to the greatest increase. So can someone tell me what this is equal to on the right? You meant, do you know? Can you tell me what the guy on the right is equal to? Okay, good, thank you. Great. I told you guys, this is a bird course. Please enjoy it while it lasts. Good. Very good. So, since gradient of f is normal to this, it means it's so it belongs to the orthogonal complement, so it belongs to the orthogonal complement. So we just proved that the gradient of f can be given by the span of the gradients of the constraints. Okay, which is the picture that Abby also talked about in the beginning, that the gradient of f needs to be parallel to the constraints because of level set results. In other words, gradient of f can be given by the linear combination of the gradients. And that's Lagrange multipliers for you. All right, so we'll do an example now. So suppose you have a box, you work for Amazon, and they tell you, I have done amount of paper A, and make the best out of it. Make a box that has maximum volume given that amount of cardboard surface area. What would be the best size for the box? So we want to maximize the volume of the box or minimize it. Our constraint is the area, surface area. Yeah, so this is the constraint. We live in the real world, so you cannot have negative length. And because we're used to of convexity, it's more intuitive for humans. We're going to look at minimization. All right, so let's do that. So our problem is minimize this function given this equality constraint. Whenever you see that, the first thing I want you to think about is Lagrange multipliers. Next week, we're going to do inequality constraints. But for now, whenever you see equal, Lagrange. All right. So let's do it. We want to find the local min subject to the surface area equaling exactly A for the box. Okay. So the theorem is that your gradient needs to be parallel to the gradient of the constraint. So you just compute. So this over here is gradient of x, y, minus x, y, z. Okay. Can someone tell me the first component? What's the first component? What do you think? Huh? No, wait. What do you think? Anybody? Do you know? Minus what? Yes. So that's the constraint. And wait. I wish I didn't. I wish I just asked you. Okay, anyways. So if lambda is 0, you get a contradiction. You get that this guy is 0, which will give you that one of the lengths is 0. Actually, all the lengths. Or how many lengths? If lambda is 0, y naught or z naught, x, at least 2 of them, right? Right? Who cares? At least 2 are 0, right? Because y naught, z naught is 0, x naught, z naught is 0. Anyways, yeah, you need at least 2 of them to be 0. So lambda, the Lagrange multiplier, is not allowed to be 0. Okay, zoom. Good. So you just isolate. So I just isolate it left and right. And of course, you also have the surface area constraint. And I mean, okay, I'll go through it, but it's just a bunch of algebra. So I add the first 3. So shall I do it? I'll do it over here. So 2 lambda, and then it's another 2, right? So it's 4. Y naught, z naught, right? Yeah, whatever. X naught equal to y naught, z naught, and x naught, z naught, x naught, y naught. But then by definition, this is a over 2, right? So these are the 3 equations, and I'll use the last one over here. Okay? Why are we doing this? By the way, you will need it for homework 1. For the, yeah, whatever. So Because this is just the perimeter of the, yeah. Okay, anyway, so you do this and then we clean it up a bit. Okay, so then what do I want to do? Oh, I see. Yes, I remember. So, okay, fine. Because this is very annoying. I need to give you each of the x naught, y naught, z naught. You know what? Next time I'll do this with linear algebra because this is a 3x4 system. I can put it in a matrix. This is overkill. I don't know why I did this one. Anyways, yeah, if you can use linear algebra, do it. This is disgusting. So here's a trick. Yes, I added x naught, y naught, but I got the same guy on the right. So I'm forced to have the following constraint. I'm forced that the first two lengths are equal. And you can imagine this is a box, you will get the same thing for z naught. So, so you get this, and now let me get you the length. So again, it says that the best one is just the cube. So cube maximizes volume for a given area. Okay, and we just did it. We had this equation, right? What is it? Oh yeah, it was over here. So we have that from here. You put them together, so it's 4 lambda 3L is equal to A over 2. Okay, so that's how I got that. And if you solve that, you get, okay, whatever you want, I don't care. So sure, I like it my way though. I don't know why I did it this way. You can solve it and yeah, you will get this equation. Oh, I see, because I didn't want the lambda. All right, fine, no problem. Anyway, so you want, if Bezos asks you, it has to be a cube of length square root A over 6. Good? Yeah. Or Elon, I don't know, whoever. Do they use boxes? I don't think they use boxes. Yes. You would be amazed some of the stupid questions they ask in interviews. It's like, and it's geometrical. Like you should look up Elon Musk's question. It's basically a tangent vector on the Earth, and they ask you to find like what's the tangent space on the North Pole and the South Pole. Anyways, it's the same. It's questions like that. It's very nice. All right, I'm moving too fast. I need questions. All right. I guess I'll do more examples on Thursday. What can I say? Okay, let me slow. So, so I gave you the minimizer. So in other words, I gave you the max volume. So now, if you remember, to get global min, global max, you need the Hessian, right? So just because, like in your quiz, you had a saddle point, right? You had 3 points. One of them was stationary, but it was neither min or maximum. And to check, you had to compute the Hessian. So you have to do the same stuff here. So there's no different. Again, you have your constraints, some simplex. And yeah, you have some simplex. You have your local min. you have the theorem we just proved that to be a local mean, the greatest increase needs to be parallel to the gradients of the constraints, because these guys are normal to the level set. All right. And you will also need the following guy, this matrix of Hessians. It needs to be positive semi-definite. Okay. And I will do it both ways. First, I do the easy one where local min implies this, and I will prove that if you have this, you get local min. Okay, good. All right. So the proof is very complicated. We'll go slow. So again, we have part one. So I'm not going to prove part one. I'm going to prove part two. And this is the proof will be the same as the one we did, I don't know, last week with convexity. Yeah, the stuff we did with convexity. The proof will be the same. All right. Again, we're talking about tangent spaces, so there's no other way, unfortunately, because x naught might not be a regular point, so I have to use differential curves. So I use x of s. So to be clear, x of s is in the manifold, and x dot s at 0 is a generic element of the tangent space. Okay, that's the context. And first one is chain rule, and the second one is product rule. Okay. Let me remind you the second order Taylor expansion in R1. So G of S minus G of 0 is equal to G prime at 0S plus a half of S squared G double prime at C, where C is some number between 0 and S. Okay. So this is the mean value theorem, NVT, second order. Is that okay? What? Good. Yeah. Good. So you apply this theorem, and this is the theorem. We apply it for x f of xs. So you have first derivative, second derivative. Let me do it here as well. So this guy, what did we prove about it? When x naught is a local min, this is equal to what at s equals 0? What do you think? What is it equal to? You can use your hands. It's a gesture. Zoom people, do you know what this equals to? Because I'm getting quiet here. Zoom? Anybody? Huh? 0, yes, thank you. Very good. So that means that, that this guy here is dead. The first term is 0. Okay. Good. Uh, Can someone tell me how can I get that the second term here is non-negative? Oh, okay, I already have it. Never mind. Follows from being a local min. Okay. All right. So you get non-negative, and let's apply chain rule. Okay, fine. I want to do it this way. No problem. Okay, so x of s is in the manifold. So hi of x of s is 0. So we do this dirty trick. We plug it in the function. Okay, so we go from here to here because we know that hi of x of s is 0. This is just a computational trick to make our life easy in computing this double derivative. Okay, you will get some gradients, right? And we will use the Lagrange multiplier theorem to clean it up. Again, let me remind you what we're proving in case you're completely lost. I want to prove that, where is it? Yeah, I want to prove that this whole expression is positive definite, right? So that's why I plugged that in. I plugged in the h's because I want to get an expression for both, right? Okay, we'll come back to it. So we apply chain rule to this expression. So if you apply chain rule to f of xs, you get this stuff, the first terms. So this comes because of this. Okay, and the second two terms come from double derivative of gradient of h of xs. Okay, all right. So let me do it like this. Keep it clean. All right. Now let's, I cleaned it up. I put in the summation. Is there a question? By Lagrange multipliers, so that's why I plugged in the h. This guy is dead. This whole term. And I'm left with this guy, which is what I wanted. So can someone tell me why am I done? What? So I wanted to prove that, call this guy Hessian. I wanted to prove that v dot v is non-negative for all v in the tangent space of x naught. So why am I done? Yeah, I'm not going till I, this is like the main thing I have to know. If nobody follows, I have to like bring it, yes. Okay, does anybody else know besides her who took 337? Like, I need to know if other people follow, because this is crazy. Do you understand? Can you tell me why it follows? Anybody there? Daniel, are you there? No?
Yeah, I'm there. Is it because s squared is non-negative? And then we have like the expression for positive definite?
Yeah, but can you like, yeah, but can you tell me how I get this guy? For all v in the tangent space? Like we're proving that, we're proving that h is non-negative. So how do we, what's the connection between this expression and this one? Yes. Yeah. So all the V's are where the form X prime 0. That's all I wanted to hear. All right, and then that's it. So you're left with this expression, and from here you just divide by s squared. And if, as you take the limit, whenever you see little o, that just means that limit as s goes to 0 of os squared over s squared is 0. That's the notation of little o. Okay? Great. All right, so I proved you that if it's a local min, then you have positive definite. Now we're going to do the converse, as we did with convexity. So if you have some constraints and you have Lagrange multiplier and positive definite, but you need it to be positive definite, not semi-definite, then x naught is a strict local min. Okay. In other words, yeah, you can solve the problem just like you did in the quiz. So you show a matrix is positive definite. The hard part is finding the lambdas. Yeah, that would be hard. You'll see in the example. That can be tricky. All right, let's prove it. Hopefully, yeah. Oh, that's another beautiful thing. We didn't talk about regular points. But of course, checking the second condition is a nightmare if you don't have regular points. So just to remind you, we proved that for all points, T of x naught m is contained in all the V in Rn, such that a number of HIV is 0 for I 1 to K, right? So if you can prove positive definite on the bigger space, where it's much easier, then you get positive definite on the smaller space, right? Does that make sense? So in other words, you don't have to show that a point is regular to use this theorem. Okay? Does that make sense? Okay. I'm just trying to make it easier. So, because in our problems, computing the this guy with the normals is way easier. And all you have to prove is that this guy is positive definite on that bigger space. So you will get it on the smaller space. So same on Tx naught m, which is hard. This is easy. Okay. If there is one lesson you will take from this course, is to always come back to this tangent space when you do optimization. That's the main thing. Yes, Tx naught m can be very, very hard. Whereas for Tx naught, you just have k equations. All right. So again, I'm going to prove that given those constraints, my x naught is a local min. I prove local min implies them. I'm gonna do the converse, which is much harder. But we did it last week with convexity. So if you understood that proof, this will be easy peasy. All right. Question number 1. Suppose this guy is non-negative. How do I know that I can put a lower bound AV squared? So we did this and I explained it and I took like 15 minutes explaining it. What? Yes. So this A was a minimum eigenvalue and the V's were eigenvectors. Okay. So review the linear algebra argument from last week. Okay, it was the same thing. So this A was lambda 1. All right. Yeah, so we're working in the tangent space. So that means I have to look at derivatives of curves. Take your guide to be unit speed. If you work later on, this is called a unit speed geodesic. Let me throw you some words in case you come back to the slides. Okay. This is called a geodesic. If you see this word, and I mean, I don't know, is anybody going to data science or am I just talking about? Well, of course you will. You're going economics. What do you think you're going to do in grad school? It would be like neural nets or like in the bank, people run neural nets. You guys are stuck with math for life. I'm sorry to say, it's unfortunate for you. Good for me because it's fun. That's fun. We do Taylor. We talked about this. And again, let me not repeat. This was 0, right? We talked about that. And we just showed, yeah, that this guy is bigger than AV. So that's basically what's going to happen. So I'm going to show that this guy is non-negative. So I'm going to get you that f of xs is bigger than f of x naught. So x naught is a local min. That's basically the argument, which we've done about 10 times. This guy is 0. So I can put it in. So I put it in. Same chain rule, product rule from before. And again, Lagrange multipliers tells you that the gradient is in the span of the HIs. This guy is 0. And this guy is positive definite, so we can lower bound it by this whole expression by x dot x dot square. Okay, so yeah, we killed off the gradient stuff, and we talked about using a speckle theorem. You can get a to be lambda 1. Okay, I remember you asked this a long time ago, so this is why. But you're on your laptop, so don't worry about it. So this is the lambda 1, and but it's norm 1, so you're just left with this expression, and yeah, so yeah. So how do you finish from here? Let's see. How do you finish from here? So let's see. Oh no, there is no S. Where there is it? So this guy goes to 0. So you basically get, yeah, this is correct. So you basically get S squared A over 2, which is strictly positive. Okay, so as long as S is not 0. All right, of course, if S is 0, they're equal. Does that make any sense? Is that okay? So I proved that X naught is a local min because if you give me any curve close by, so let's go. It's hard to do it. I'll do it in 1D. Hopefully it makes sense to you. So this is 1D. This is the X naught. XS is always in the domain. And it says that if you look locally, you have f of xs is bigger than f of x naught. Okay, so you sample from there. Is that okay? Okay, I don't know. Yeah, you can tell me. I don't know. Good. All right. So do I have an example? We don't have time. I'll do it next time. So I will prove you that the unit cube is the perfect box for Bezos. Okay, I'll see you next. Thank you. Yes, might go into data science. That's great. Good to hear. Economics, of course, you're gonna do now. Where are you going? Are you not doing data science? Huh? Like quants, right? Oh, okay, okay. You mean what was your area again? What's your area? What are you studying? Yeah, I mean, you can absorb it. Yeah. Yeah, no, I will be part of that, right? Or in Q. Okay.
So which one do I follow?
No, whatever you like. Honestly, I'm not really. Even if you doesn't have to be the book either. If you find something in your textbook. Yeah, either one is fine. Which no, you were on your laptop, and I was like, because you mentioned about the local min, the eigenvalue. I came across the minimal eigenvalue step. I remember you asked me a question. What?